This is in preparation for calculus inverses, but today is just pre-calculus inverses. But that said, I felt like a little review is important. So this is a green paper because it's a pre-calculus kind of lesson. This is the stuff I expect you to be able to do. I expect you to be able to find an inverse numerically, analytically, and graphically. Numerically is super duper easy. Say you have this table of x and f of x, and I asked you to graph the inverse function. Do that quickly, and it should take, if you know what you're doing, it should take about 15 seconds, 10 seconds. I keep forgetting the words. All right, are we ready? Okay, here's pictures. Hopefully, okay, sorry. So give me the row of x's. 7, 11, 4, 2, and the row of x at inverse. Okay. So the big idea of the day is when you find the inverse, you switch x and y. Yeah? Right? Right. Okay. If I asked you then to do an inverse analytically, say I asked you to find the inverse of f of x equals 2e to the x plus 3 implicitly and explicitly. Well, surely then it's hard to do implicitly and explicitly if you don't know what those words mean. Implicitly means the inverse is implied. You don't have to solve for the inverse. You can leave it just all mixed up. So, for example, the inverse should take one step. I just switch. X equals 2e to the f inverse plus 3. Now, I am aware that students prefer y instead of f inverse notation. I prefer f inverse notation. Here's why I make my case here. If I have this, then when I do the inverse, it's here, and there is absolutely zero difference between the look of those y's. Okay, there's no communication as to this is the original, this is the inverse. They look both like y to me. But if I use inverse or function notation, then when I find the inverse, there's a notation for, hey, this is now the inverse, not the original. And they look different. That's why I prefer function notation, although I'm sure you will continue to use y. I am a little, you'll find that I'm a little fast and loose with my arguments on the inverse. It technically is f inverse of x, but you'll see me write f inverse often just with no argument, which is probably bad math, but that's why my teachers were crazy for my work. They hated it. That's all right. Now that's implicit, okay? That's the inverse. I found the inverse because I switched. It's implicit because it's not solved for. The inverse is implied with it. But if they ask for explicitly, then I then have to solve for the inverse. So, how would you, this is implicit, how would you find the inverse or isolate the inverse? 3 steps, go. Subtract 3, divide by 2, natural log. So f inverse is, this is big boy math, so you can do all those at once. What is it? The order matters, obviously. Natural log of x minus 2, x minus 3, all over 2. Okay? Okie dokie. Now, say you are given, this is more common like you see in the book, and it's good preparation for the calculus to come. Say you're given this cube. And if I ask for f inverse at a specific point, f inverse at 1, this is the thought process I would like you to go through. F inverse, oops, sorry, right, and this should be F inverse at x, excuse me. F inverse at x would be just x equals F inverse cubed plus F inverse plus 1. Wouldn't you say that when we do the inverse, we switch? We? So far, so good? So far, so good? Yeah, more energy, people, more energy. All right. Now, when they say F inverse at 1, that is an x value. So you're putting 1 in for x in your inverse. So that 1 goes there. 1 equals F inverse cubed plus F inverse plus 1. Now, to solve for that then would really involve some solving a cubic if you were expected to. If you were expected to, you could have to solve cubics, but no calculus teacher is going to go that far back in the pre-calculus. That's not worth my time. All right, so we're not going to be solving any cubics. It's by guess and check. What F inverse value would make that true? 0. I mean, can't you just look at it and say, yeah, they have to be 0, yeah? Now, you might be thinking, wait a second, couldn't a cube have 3 solutions? And do I have to do synthetic division and the rational roots theorem and Descartes' rule of signs and love and the glove? And do you remember all that stuff? Me either. Good stuff. So you don't really need it for calculus. I got to say, we don't do that stuff. So it'll be by guess. So that said, do those two, please. In the same kind of fashion. Although I guess you can bypass the inverse step because that's the same. Okay, so just go to the second and third steps. If you prefer to use y instead of f inverse, you sure can. Ready? Wait. So if I put, in this case, the inverse is the same as we said. When I switch, it's the same function. That's the same. In this case, then you're saying 3 equals, I'll just use y this time, y cubed plus y plus 1. Guess and check, that must be 1. So f inverse at 3 is 1. What about f inverse at negative 9? 9 equals something cubed plus y plus 1. Negative 2. Yeah, f inverse at negative 9 equals negative 2. I think we can see it's going to have to be a negative, and negative 1 isn't big enough. Negative 2 works. Okay? You understand what I need you to be able to do? All right, then, graphically, let's talk inverse in its graph. Y equals x plus 2 squared. Speak some math to me. What does it look like? It's a parabola shifted to the left 2. What's the math word for shifted? Translated. Nicely done. Translated to the left 2. Okay, so it's a parabola translated left 2 or shifted left 2, like most people say. That's the function. The inverse. As a fallback, you can always do the old switchy switch of points. So if you get confused, fall back to that safe spot of I just switch x's and y's. So for example, if negative 2, 0 is a point on the original, then the inverse would use 0, negative 2. If negative 1, 1 is a point on the inverse, or of the original, the inverse would involve 1, negative 1. And so on. This point over here is negative 3, 1, it would become 1, -3. So we get a graph that looks like that, yeah? Didn't really show, that should be -2. Where's the symmetry? Okay, when you do an inverse, what do? Switch x and y. Take your fingers and do this. Switch x and y, then it reflects over y equals x. The inverse is a reflection across y equals x, because you're switching the x and y axes. It'll reflect right over that line. So there's symmetry about that line. Notice that the inverse is not a function. Why is the inverse not a function? It fails the vertical line test. So what attribute of the original caused the inverse to be a failure? If the original, the square, that's absolutely true. If the inverse fails the vertical line test, then it must be the case that the original failed the horizontal line test. That is to say, it wasn't one-to-one. We'll come back to that in a minute. All right, then. So I also need you to understand some relationships between a function and its inverse. So let's start with this. F of x equals the square root of x plus 2. Easy enough. Find the inverse. I want to find the inverse explicitly, which is to say, I want you to solve for F inverse when you switch. So what is F inverse? X minus 2 quantity squared. Okay, x minus 2 quantity squared. All right, then. Wish I would have chosen better. Yeah, unfortunately, that's not invertible. That stinks. That's not a good choice. Scratch that. Scratch that. And let's go with natural log of x minus 2, please. I want this to be invertible. I'll get to that other idea later. Invertible is to say that a function has an inverse that has a perfect reflection of domains and ranges in all points. So I'll talk to that in a minute. But what is the inverse here? X equals log of f inverse minus 2. So I'm sorry, let's go it again. I switch and I get x equals log of f inverse minus 2, yeah? So now solve for f inverse. E to the x plus 2. Is that plus 2 inside with the x or after the function? After. Okay, so f inverse is e to the x plus 2. Okie dokie. Now, if you are to prove there are inverses, inverses by nature are supposed to undo each other. So if you take 7 plus 2 minus 2, you get 7. If you take 8 plus 2 minus 2, 8. If you take 10 and log it and exponentiate it, you're right back to 10. So the idea is that they're supposed to undo each other. That's what makes them inverses. And you're right back to where you start. That said, then, you can prove things are inverses if when you do one, then the other, you're right back to where you started, which is x. So if you were to prove they are inverses, then you actually have to do two things. I have to show that if I put f inverse into f, that I get x. Now, that means that in f, I'm putting that guy, yeah? Are you with me? Okay. And if I put that guy into f, then that means the natural log of blank minus 2, because that's what f is. And in that blank, I put e to the x plus 2. Well, if we simplify within, the 2's go away, and I get natural log of e to the x, which is just dot, 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 x. Okay? Try the other one then to show that really has to be invertible, or both ways. So you need to show that now if you put f into f inverse, it also is the case that they undo each other. So into the inverse goes the original function. The original function is log of x minus 2. Now I put that into the inverse. So I look at the inverse and I say the inverse is e to the blank plus 2. And in that blank, I put f. E to the log, cancel each other out. Get x plus 2 minus 2, which is just f. All right. Okay. Last, find the domain and range of f and f inverse. So for f of x, let's look graphically. What's the graph of the natural log function, and then what is the 2? Takes the natural log function, which looks like, give me some action here. There you go. And then which way? To the right 2. You should focus on the vertical asymptote being shifted right 2. And that x-intercept, which is normally at 1, will now be right 2, so it'll be at 3. And so the graph of f looks like that. What's the domain? X is strictly greater than 2. What's the range? All reals. Okay. Now, f inverse we found was e to the x plus 2. What does e to the x graph look like? Thank you, Ethan. And then what does the 2 do? Shifts it up 2. So instead of having a horizontal asymptote at 0, we'll have a horizontal asymptote at 2. And instead of having a y-intercept at 1, we'll have a y-intercept at 3. And the graph will look like that. If I put those together, they would be what kind of reflection? Cross y equals x. What's the domain of the inverse? All reals. Goes forever left and forever right. What's the range of the inverse? F inverse is, or y I suppose is, greater than 2. Now, the idea then is, makes total sense. If an inverse involves switching x and y, then the domain becomes the range, and the range becomes the domain. So you can see the domain of the original becomes the range of the inverse, and the range of the original becomes the domain of the inverse. Okay? Assuming it's a function, and that's a bit of an assumption. So here we go. You often want the inverse to be a function, okay? Why? I mean, you might say, who cares? You should care. If I say, hey, what's the inverse cosine of 1/2? Do you want to be listing things forever? No, you want to be saying, hey, it's just blank. What's the inverse cosine of 1/2? Don't make me cry. All right, that's okay, because I'm going to make you do 18 of them in the bottom. So it's pi over 3, by the way. So let's go to this. I want the inverse to be a function in many cases, and the only way that's going to happen is if we restrict. Remember earlier when we talked about the parabola and its inverse, this most definitely, this inverse was not a function. And that's because the inverse fails the vertical line test, which we said that can be traced back to the original failing the horizontal line test. Now, the words for that then is that the original function, if the original function fails the horizontal line test, then it's not 1-to-1, which is to say for every one x there is exactly one unique y. No y can be made by two different x's like is happening here. A function is one-to-one if and only if, that's what IFF stands for, any y value can only be made by one x value. Consider this. If a function is one-to-one, its inverse will be a function. That's easy. Think derivative. This is the only calculus I have in here. A function will be one-to-one, which is to say it'll behave in a way that is only one y value for every x value if the derivative is monotonic. What the heck does that mean, monotonic? What? It's one sign is what it means. Now, if the derivative is monotonic, it's one sign. Why would that be important for the derivative to be one sign only, either positive or negative? Well, if there's a sign change, then what would happen? Yeah, I mean, you're talking no more one-to-one, yeah? So if the derivative is monotonic, or one sign only, then the function will be one-to-one, and the inverse will be a function as well. What about sine? Is sine one-to-one? Does it pass the horizontal line test? No, most definitely not. It fails the horizontal line test forever, so that's a no. What about tangent? Is that one-to-one? That's a big no. One curve passes the horizontal line test, but there isn't just one curve. There's infinitely many curves, and so it's a no. What about x cubed plus 1? Yes, that is a yes. What about this cube? This is also a cube, and it has zeros at 0 and 1, bouncing at 0. Yes or no? No. Okay. What about the absolute value of x? No. Fails the horizontal line test, so the inverse would fail the vertical line test. And what about e to the x? Yes, that's a yes. Okay? All right. Now, it is sometimes the case that you get one of these no cases and you want it to be a yes. Well, the only way you're going to make this a yes or make it one-to-one is if instead of allowing sine to go forever, you say, you know what, I'm only going to let you do this much of the graph so that it passes the horizontal line test. So, for example, if you had sine of x, which normally looks like this, and more, obviously, then we want to restrict the domain, or the x's, so that it passes the horizontal line test. Now, if there's no direction, then I suppose we could all go with different numbers. I mean, one person might say, I'm going to take only this piece from pi over 2 to 3 pi over 2. And another person might say, I'm going to do this piece from negative pi over 2 to pi over 2. In terms of ease, it's probably best to keep as close as you can to the origin and make it as continuous as possible. So, for example, you might restrict sine to only negative pi over 2 to pi over 2, so that it's close to the origin, that it gets all its negative and positive values, and yet it doesn't fail the vertical line test. What's the inverse then? That's a really easy case. Did I miss something? What's going on? Oh, those loud sounds. You guys are worse than seventh graders. Holy cow. Easily distracted. Are you with me? The inverse is just the inverse. Cool? So tangent. This normally looks like this. And so on. So what would be a logical restriction to this? Again, trying to stay as close to the origin as possible. Pi over 2 to negative pi over 2 to pi over 2. And what about parentheses or brackets? Parentheses, because we have asymptotes at pi over 2 and negative pi over 2, so that's silly. The inverse then would be arctangent. By the way, I'll use those interchangeably. That is the same as arctangent. You'll see one, both. It's the same. Okay? Uh, absolute value of x. That fails the vertical line test, right? Now I want to restrict the domain so that I have a one-to-one passing, horizontal line test passes. And I want to get all the y values I can. So what would you do to restrict the domain to? 0 to infinity. Okay. Then you're only dealing with the right-hand side of the graph, and all is well. The inverse then, bit of a trick. Inverse. So if you restrict it to this, then what's the function? X. So what's the inverse? X. Crazy picture. What about y equals x minus 2? Right, 2? And so restrict it so it passes the horizontal line test. What do you want to do? 2 to infinity? Oui. And the inverse then would be what? What is it? Square root of x plus 2 inside or outside? Outside. Okay. That would look like this. You can see it. Okay. All right, then. Last but not least, trig. All 6 trig functions have to restrict the domain in order to pass the horizontal line test. So we talked about how sine looks like this, but I would restrict the domain so it was only this. The directions that I'm giving you are sketch the graphs of each, darken the restricted domain, say I'm only going to allow it to here so it passes the horizontal line test. Then graph the relation, or the inverse relation and darken function. Now, that said, I'm saying this. This is the inverse. It would look like this. But that is most definitely not a function. So if I worked on only the restricted, then the restricted is here. Now, I know it's been a while, but do you remember that stuff? Okay. Just so we're clear on the scales, what's on the horizontal scale of the original graph? Angles or side ratios? Angles. It's pi over 2 here, and max opposite to hypotenuse ratio of 1 there. So on the the inverse, it's 1 on the horizontal and pi over 2 are angles on the vertical. As we switched, yeah? Okay, so cosine looks like this, and so on. How shall I restrict it so it passes the horizontal line test, gets all possible y values, and close to 0? Restrict it to only 0 to, I need to get to its minimum, so pi. Okay? So I'm going to restrict it to 0 to pi so that when we invert it, instead of crossing the y-axis at 1, it's going to cross the x-axis at 1 and it'll look like this. When we invert it, I will only, instead of be taking x's from 0 to pi, I'll be taking y's from 0 to pi. Okay? See what I'm looking at? Try the other 4. See to what degree you remember those. Tangent. tangent, instead of having vertical asymptotes at negative and positive pi over 2, it'll have horizontal asymptotes at negative pi over 2 and pi over 2. And it'll be just the middle section. That shape, by the way, makes for super duper modeling. You use that shape in a lot of approaching and upper limit kind of things, like learning curves and such. That shape of inverse tangent is, along with cubes, cube roots and stuff, is pretty useful in modeling. Okay, then the ones that really stink. Here we go. Geez Louise. These are terrible. All right, so here we go. Just do it. Here's sine, yeah? So what is... We're about to graph the inverse of the reciprocal of sine. So first, what's the reciprocal of sine? Cosecant. And the reciprocal idea is wherever sine has zeros, the reciprocal has vertical asymptotes, right? Kind of wish I would. That's right. It's good review. Okay? So that the reciprocal would be this. Now, is that a function, a one-to-one function? It is not. That stinks. So I need to limit the domain so it's one-to-one. What about on the positive y values? I only need to take half of those curves. And if I take the part that's close to 0, I'll take that piece. I need some negative y values. And so in order to get those, but try and be continuous and close to 0, I'm going to take those, yeah? So now, when I do the reciprocal, instead of horizontal asymptotes at 0 and pi and negative pi, I'm going to have horizontal asymptotes there. And this point here is crucial. It's pi over 2, 1. So on the reciprocal, it's 1 pi over 2. Now that cup was going up, so on the inverse it'll go out. And this point that was at negative pi over 2, negative 1, will be at negative 1, negative pi over 2, and be a cup facing out. But then the restrictions. Take chunks close to the axis, and we're only going to use those. Follow? So it's negative pi over 2 to 0, and 0 to pi over 2. Oy, oy, oy. Okay. Cosine looks like this. Asymptotes there. And secant curves here. Ah, shoot. Oh, well. Right? Now, we talked about how on cosine we went only from 0 to pi. So our inverse will be only from 0 to pi. So we're going to restrict it from 0 to pi. So the inverse then will be kind of, what's this? Let's start with this point. This point was 0, 1. Now it'll be 1, 0. Instead of an asymptote at pi over 2 vertically, we'll have one horizontally. And it'll go like that. And that at pi. Sorry, I'm starting to rush. What about our cotangent? Our cotangent. Cotangent looks like this. Do you remember that? Or no? Okay. Okay, cotangent is 0 to pi, is the restriction. So the inverse then will look something like what? What would the inverse of cotangent be? Instead of a vertical asymptote at pi, you'll have a horizontal asymptote at pi. Instead of crossing at pi over 2, 0, it'll be at 0, pi over 2, and then the bend. Does it go up to the right or down to the right? It does go down to the right because it approaches the positive y-axis, so it should invert and approach the positive x-axis. Okay, let's see how good you are. In these, take the first row, I went soft, they're all positive. Tell me what they all equal. Go. You should be able to do those in 5, 10, 15, 20, and 30 seconds. All right, that's got to be 30 seconds, yes? Okay, cosine, inverse cosine of 1? 0. Okay? Now please understand that these are restricted domains. You should be only giving answers from 0 to pi, and the only thing that counts is 0. So if you said 2 pi, no, 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 no. One answer, and it's 0, period. Not 2 pi, not 4 pi, not anything else, 0, only. Inverse sine of root 3 over 2. It is pi over 3. Inverse tangent of 1. Pi over 4. Inverse secant of root 2. Pi over 4. Inverse cotangent of root 3. Pi over 6. I agree. Pi over 6, yes. Cosecant of 2, which would be like sine of 1/2. Pi over 6. Okay. Now then, when you do a negative, those are all first quadrant, yeah? So if you see a positive, it's first quadrant, no doubt. These, you're going to have to think which quadrant. It's either, this is really what I should have done in that above section. If you do inverse sine, it's got to be first and fourth, negative pi over 2 to pi over 2. Inverse tangent is negative pi over 2 to pi over 2. And inverse cosecant are first and fourth quadrants. That gets you positives and negatives of all those. But for cosine inverse, you would need to get negatives in the second quadrant. So you're looking at those. So pay attention to what quadrant and try those next 6. All right. I asked myself, what's the reference angle and in what quadrant? So cosine makes a half at pi over 6 or pi over 3? Pi over 3. Okay. If cosine is negative, then it's in the second quadrant. So what's pi over 3 in the second quadrant? 2 pi over 3. Okay. Inverse sine. Sine makes -1 at negative pi over 2 or 3 pi over 2, but in the appropriate frame is negative pi over 2. Remember, sine is restricted from negative pi over 2 to pi over 2. 3 pi over 2 would be way up here. It's definitely not part of the range. So what about inverse tangent of root 3 over 3? Tangent makes that kind of side ratio at pi over 6 or pi over 3. Pi over 6. And then what quadrant? Tangent's negative in the fourth quadrant, so that's negative pi over 6. Inverse secant of, that's like a form of root 3 over 2. So cosine is root 3 over 2 at what, pi over 6 or pi over 3? Pi over 3. Secant is negative in the first or in the second quadrant. So pi over 3 in the second. Did you say pi over 3 or pi over 6? Sorry. Pi over 6 in the second quadrant is 5 pi over 6. Okay. Inverse cotangent of 0 would be, I guess you could say it's like where tangent is undefined. Where is tangent undefined or cotangent is pi over 2. Remember, you're talking cosine over sine. Cosine is 0 at pi over 2. Cosecant of root 2, that's like sine. Root 2, I see pi over 4s. So pi over 4 and negative would be negative pi over 4 because sine is in the first and the fourth. Okay, how'd those go? All right, and then these problems are pretty good practice for the calculus to come and pretty common on other calc or trig books. So if I asked you for the sine of the inverse cosine of 2 over 3, it's tempting to bust out the old calculator, but that is not necessary if you just draw. Okay, this is a triangle with the adjacent side 2 and the hypotenuse 3. Because it's positive, it must be first quadrant. So if I draw a triangle with adjacent side 2, hypotenuse 3, and then say, all right, now take the sine of that. Well, to find the sine of that, I would need the opposite in the hypotenuse ratio. So I need to find the opposite. How do I find the opposite? Pythagorean theorem. The square root of 9 minus square or 2, 9 minus 2 square rooted. Whatever. You get the idea. It's the square root of 5. You know what I mean? So what's the cosine of that angle? Adjacent opposite hypotenuse is root 5 over hypotenuse 3. Okay. So the idea is you draw a triangle in the appropriate quadrant, find the missing side, and then answer the question. So for this, if I draw in the appropriate quadrant, inverse sine that's negative must be in the fourth quadrant. The opposite side is -3. The hypotenuse is 5. So far I have that information. If I find the adjacent side, it must be a 3, 4, 5. That 4 is positive because it's on the positive x-axis. Now I can take the tangent of that triangle. What's the tangent of that? Opposite to adjacent, TOA, -3 fourths. Try the next one. Oops, that's not possible at all, is it? My bad. Let's call that, sorry, that's not possible. Inverse sine of -2/5. Okay, sorry about that. So did you get a triangle with the fourth quadrant and the adjacent side root 21? Okay? If tangent is opposite to adjacent, then cotangent is adjacent to opposite. So what's the adjacent to opposite ratio? Root 21 over -2. Okay, last one leads to that last one. I remind you, work inside out. That one's a little different. You don't need to draw a triangle. Answer? It is pi. Okay. Sine of negative pi over 2 is -1. Then you're saying, all right, at what angle is cosine -1? And that is at... Okay. Sorry that took so long. Talk on it. Questions on... What do you got? Piece about 56 and 57 or just 56? 57. Just 50? You do have 56? Okay. I need 56 by the end of the day. I'll answer whatever questions I have time for. But the key is online, but I do need 56 today. I don't want to get 3 backed up. So 56 questions real quick. 1. Okay. I will cut you a good deal of slack as long as you attempted every question. Number 1 was tough. You've got a package with square ends, so call it x by x by y. And the 3 dimensions cannot exceed 16 feet. So let's say that we use the biggest possible. X plus y can only equal 16 or less. If I want to maximize the volume, then let's start with the volume equation. It is x squared y, yeah? Now we don't want to maximize with 3 variables. So what can I do with this to get it down, use it to substitute into this? Y is 16 minus 2x. If you plug that in there, then you get x squared times 16 minus 2x, or 16x squared minus 2x cubed. Now you can maximize the volume by finding v prime positive to negative. The derivative is nice and clean and should go. Okay, that should get you started. Other things that can get you started on? 17. 17 is something like x squared over 9 minus y squared over 4 equals 1. Shoot. Sorry, I will be here at 7th hour. I'll be here after school, but I do want 56 today. I apologize for going long. Did you get the derivative okay? What was the issue? Yeah. Dx, dy, dx. Surgery. Yeah, so something like negative 2x over 9 times negative 4 over 2y. And then plug in. It should be.
And then just plug in?
Yeah. Okay. All right.